Stanford University.
Okay, let's go to the space-time view of string theory. What other kind of view could there be but space-time? But I mean, let's think of the blackboard as space-time and view what string theory looks like. First, let's do something simpler first. Let's just talk about an ordinary particle. An ordinary particle in classical mechanics has a trajectory. Both in non-relativistic physics and relativistic physics, the trajectory can be described by the three-dimensional position x as a function of t. But if you're doing relativity, there's something which is more convenient, and that's to take all four components, space components and time components of position, call them x mu, and think of them as a function of a variable which just denotes and demarks, let's say, proper time along the trajectory of tau. Let tau be the proper time along the trajectory. And then clearly, if you know the four-dimensional position at every proper time, or every value of this parameter here, then you can say exactly where the trajectory went. So there's a slight, well, maybe more than a slight, there's a difference of emphasis in non-relativistic physics where you think of x as a function of time, and in relativistic physics where you might be inclined to think of x mu, the four components of position, as a function of a parameter along the trajectory, a kind of scalar parameter along the trajectory. In each case, the motion of a particle is defined by an action, by a principle of least action. In the case of a non-relativistic system, for a free particle, forget potentials, nothing else, the action, which is usually called S, I don't know why it's called S, it's the same label as we use for entropy. And to make matters worse, in many cases, entropy and action turn out to be the same thing, numerically. But S is action. And for a non-relativistic particle, it's the integral over time along the trajectory of the kinetic energy. 1/2 x dot squared, and I've chosen the mass of the particle arbitrarily to be 1 because I get tired of writing it. Okay. That's the action. And what do you do with it? You minimize it. You minimize it to find the trajectory of the particle. You minimize it subject to some end positions, holding down the endpoints, you minimize it. Now that's not what you do in quantum mechanics. Before we do that, let me discuss the relativistic case. In the relativistic case, something very similar. The thing is the action can be taken to be the integral over tau, the proper time along the trajectory, of dx mu by d tau, dx mu by d tau. Notice there's one upper index and one lower index, and you can figure out what that means. In other words, it looks very, very much like the non-relativistic kinetic energy formula, but it means something different. There are four components of position, and the time is the proper time. And what's more, the time components and the space components of this expression have different sign. But apart from that, they look very similar. And again, what do you do with it? You minimize it. You minimize it subject to the constraint that at the ends of the period, the particle is at this space-time point or that space-time, and that space-time point. So there's a sort of parallel structure, and basic principle is a principle of least action. Now in quantum mechanics, you do something totally different with the action. What you do with the action, you ask a different question. You don't ask what is the trajectory given to endpoints. Here you ask what is the trajectory given to endpoints. The answer is, of course, a straight line. In either case, it's a straight line. It's a straight line through space and time with constant velocity. You ask a different question. You ask, what is the amplitude that a particle that started at this point at time 0 or at the beginning of time, at the start of the time interval, is detected at that point at a later time. That's the question you ask. You don't ask what's the trajectory in between, you ask what's the amplitude for the particle to go from here to here. And the answer is the amplitude to go from point 1 to point 2 in either case, you write the action, you write the exponential of the action, e to the I, not just any exponential, but exponential with an I in it, e to the I times the action, let's write it out explicitly, d by dt over 1/2 dt dx by dt squared. This integral here goes from t1 to t2, but then you're not finished. You're not finished. This expression depends not only on the position of the particle over here and over here, but it depends on the position of the particle everywhere in between. So what do you do with it to find the amplitude? You integrate or you sum over all possible trajectories. Sum over all trajectories. Or integral, strictly speaking, over all trajectories. This is a monstrously complicated thing. It's not a simple integral that you can put on, what's his name's? Mathematica. It's an infinite dimensional integral, a continuously infinite dimensional integral. So it's a mathematical monstrosity. I mean, but this integral over here is just the integral along the trajectory. That's easy. That's just the action. But this integral over here is the sum over all trajectories. So the particle feels out all trajectories. It doesn't sample the one of least action. You integrate over all of them this expression to find the amplitude to go from 1 to 2. That's the quantum mechanical version of the principle of least action. It's Feynman path integral. You do the same thing in either classical non-relativistic physics with this expression or relativistic physics with that expression. When you calculate in relativistic physics, the amplitude to go from 1 to 2 is called the propagator. It's called the propagator for the particle to go from 1 to 2. And you do some fancier things with it. You, for example, consider processes where particles come in, join, split, and go out. A similar kind of action is defined in terms of the action for each one of these, what should we call these? Each one of these segments. You add the action together for each segment, and then you don't sum over just a single trajectory, you sum over all of these trajectories, and on top of everything else, you integrate over the points where the trajectories came together. So you do the same kind of thing, and it gives you a Feynman diagram. And then at the end, to make the whole thing even more complicated, you sum over all Feynman diagrams for a given process. And that gives you the amplitude, not for a particle to go from one point to another, but for a pair of particles to come in and go out. All right, that's the basic setup of Feynman path integrals. Before we go into string theory, let me teach you a trick that physicists use over and over again. It's a cheat. It's a cheat. Can it be justified? In some special cases, it can be justified. It turns out it can be more easily justified in string theory than in quantum field theory. But I'll tell you what the trick is. This kind of integral, this integral, is sum over trajectories. It feels out all trajectories. Let's even concentrate on the non-relativistic case. It feels out trajectories which go like this. It feels out trajectories which go like this. It feels out straight trajectories, and it feels out some wild, insane trajectories. Are some of them somehow more important than others? Of course they are. The ones which correspond to the classical motion, the straight line ones, must be the most important ones. Otherwise, classical physics wouldn't make sense. But when you look at the integrand here, e to the I times anything always has magnitude what? 1. So whatever the trajectory is, they all have equal numerical weight. They come in with different phases. The different phases can cancel each other. If you're adding up numbers on the complex plane and all those numbers happen to have unit magnitude, that doesn't mean they can't cancel. They can cancel, they can give rise to a real number, they can give rise to an imaginary number, they can do all sorts of things. But each one of their contributions is as big as every other contribution. In that case, a normal definition of an integral doesn't make sense. It doesn't converge. It doesn't converge because the trajectories, which are wildly way out there and correspond to some very, very distant trajectories in some sense, don't have smaller and smaller amplitude as the trajectory gets more and more wild. So, strictly speaking, these path integrals don't really exist as any well-studied mathematical objects. Okay, so how do we deal with them? Well, one way of dealing with them is to be extremely careful, define integrals in an extremely precise way, all sorts of reservations and things that are too hard to, even for the people who do them to think about. Really hard stuff. There's a trick. There's a trick, and the trick always works. The trick is one which, to justify it, is as hard as trying to understand the original integral. But once you've justified it, it's the trick which always works and always gives you the right answer. So I'm going to tell you what the trick is. Which shall we take? Let's take this case here, the relativistic case. You change the tau variable. And how do you change it? Very, very simply. You invent a new variable called s. And s is just any number times tau. We'll choose the number alpha later to our convenience. It's just a change of variables. This is an integration variable. Incidentally, it goes from tau 1 to tau 2, where tau 1 and tau 2 are the endpoints of the trajectory. But we change variables. Oh, this s, we shouldn't confuse this s with the action. I'm sorry I even called, let's call the action, let's give the action another name in order to avoid confusion.
You have a little s and big S, what's the difference?
You're right. Little s, okay? Little s. Little s is by definition alpha t, and what is alpha? Alpha is whatever you want it to be. We'll pick it later. All right, so let's see what we get then. dt, did I want, no, I think I'm going to be smarter. I'm going to set tau equal to alpha times s. Tau is equal to alpha. Then I don't have to invert the equation. All right, so what does this give us? This gives us integral then from S1 to S2. The endpoints now are the endpoints of the S interval. The endpoints of the S interval are, of course, just alpha times the endpoint values for the tau integration. Okay, now we have d tau. D tau is alpha ds. And then we have dx. What's dx by d tau in terms of dx by ds? Wherever you see a tau, you stick alpha times s, that's all. So this becomes dx by ds squared. I won't bother writing all the indices mu. But 1 over alpha squared. For each tau, I have to put in alpha s, so that gives me a 1 over alpha squared, so there's alpha squared downstairs. That's the action. Alpha downstairs. Now what do we do with that action? We put it up into the exponent with an I. Can you read this? E to the I 1/2, I suppose, if I want to get it right. Let's just put the 1/2 out here. Keep it out of the way. Right. The I, of course, is just a constant that can be brought inside the integral. and it's I over alpha. Now, it's complete nonsense, or at least it needs a major justification to do this trick. But what are we going to choose? What do you think we're going to choose alpha to be? I. I or minus I? Let's see. I over I is 1, right? I think I want it to be minus I. That sounds right. I over I. Yeah, I think I want alpha equals. If I choose it to be minus I, this becomes I over minus I, which is also called minus 1. And the whole exponential magically loses its I. It becomes e to the integral minus, that's this minus sign from I over minus I, 1/2 dx by ds squared ds. The only place that we have to be a little bit careful is we have to remember the endpoints of the interval here are not really real values of s. We're going to pretend that s can be a real quantity, that this integral can be treated as a real integral, even though the endpoints of the integral are not real numbers. Why aren't they real numbers? Because tau is equal to minus is, and the endpoints of the original integral were real values of tau. But let's forget that. Let's just call it from S1 to S2. And later on, we'll remember that S1 and S2 were imaginary values. Later on. For the moment, just leave it this way. Now we're going to integrate this over all trajectories. Over all trajectories. This is much better than the original integral. In the original integral, no matter how wild the trajectory was, the amplitude for that particular trajectory was in magnitude 1. Now let's take some wild trajectory and stick it in here. If the trajectory is wild, if it goes off and extends off to some large spatial separation and comes back, then there's going to be places where the x by ds is going to be very large. If a trajectory is wild in any form whatever, maybe just because maybe it doesn't even go very far, maybe it just wiggles extremely rapidly. Well, that's okay. The x by ds is going to be very, very large. It's going to oscillate, but it's going to be very, very large. Or maybe it goes off and then comes back a long distance. Still, the x by ds will be very, very large along the orbits where it goes out and comes back. So for any kind of trajectory that's far from just the simplest trajectory, namely the straight line, the action is going to be huge. It's going to be huge, and it comes in with a negative sign. E to the minus a large number is a small number. So in this form, wild trajectories don't contribute very much. Only trajectories near the straight trajectory are important. This is a form of path integral that is used in statistical mechanics. It's called the Wiener integral. It was invented before the Feynman path integral, and it's perfectly convergent. Mathematicians know how to define it in a serious way, and it's a good quantity. So this is what we are always doing. We are always making this trick of turning a time variable on its side by making it I times some time interval, time variable, and then using it in integrals. Now, what's the trick though? At the end of the day, this whole thing is going to be some function of the endpoints of the integral. You evaluate this not paying any attention to the fact that the endpoints of the interval are imaginary numbers. But then after you have evaluated it, you then The right word is analytically continue it or extrapolate it to imaginary values of S. This is something that we know how to do. It's a straightforward procedure if you actually evaluate these things. For the experts, they're analytic functions of S, and you can extrapolate them or analytically continue them to the desired complex points. This is the only real way that physicists ever really do path integrals. When you hear people talking about path integrals, either they're just talking, or if they're actually trying to perform them, they're doing them this way by turning the time variable on its side. All right, I thought I would tell you that once and for all, because we're going to do that in string theory. So let's come to string theory now. Same kind of setup, but now a particle is not a point, it's a string. Its world history is not a world line, it's a surface. It could be open strings, in which case it's a surface, a ribbon, kind of ribbon, a ribbon that can change its length and change its or way it's embedded in space, but it's a ribbon. Closed strings, it's not a ribbon, it's a tube. You can call it a world tube, usually called a world sheet. That's the motion of a particle. Let's talk about its action. We're interested in its action. Now, the kind of question we're going to ask is, given the location of all of the points on the string at some initial time and some later time, what's the amplitude to go from the initial state to the final state? What's the amplitude that if you set the string up in a certain configuration and then let it go, that you would find it at a later time at some other configuration? Now, the location of a point on the world sheet is a function x of two variables. One of them is a kind of time variable along the sheet. We'll call it tau. It's not real time. It's real time, no more real time than the tau variable up here was more like proper time. But now it's just a parameter. It's just a parameter. You take the sheet, you coordinatize it with two coordinates, sigma and tau, and you write x of tau and sigma. We've done that before. It's a function of two variables. If you know x mu for each sigma and tau, then you know where that point on the string is. And if you're given the whole history of the string as a x mu of sigma and tau, that does it. That's the whole history. Again, you construct an action. And this time the action is the immediate generalization of that, but with two independent variables here. It's s is equal to integral from, I'm not going to try to label the starting, it's too complicated to label the start and the finish. We'll just write what it is. It's the integral d tau d sigma. It's an integral over the two-dimensional world sheet of the x mu by d tau squared minus the x mu by d sigma squared. I think I have it right. The x mu by d tau squared minus the x mu by d sigma squared. That's the action for the string. And notice this is the action of a field moving in tau and sigma space. It's just the action of the wiggles moving up and down the tau sigma on the tau and sigma, but it is also the action for a tube moving through space-time. It comes from the fact that tau is, it comes from the same place. Okay, it comes from kinetic energy minus potential energy. Kinetic energy minus potential energy. This is kinetic. It's like a time derivative. This is potential energy. It's like a space derivative. So it's the fact that the action, the Lagrangian, has a minus sign, T minus V. Okay. What do you do with this action? You exponentiate it. E to the I. And then you integrate it over all possible surfaces. I'm not going to try to draw a complicated surface. Well, I tried. I failed. You integrate it or sum it over all possible surfaces. Incidentally, there's a classical version where you don't do the path integral, which just tells you if you start the string in a certain fashion and end it in a certain fashion, how it has to move in between to satisfy classical equations of motion to go from the initial to the final. But we're not interested in that. We're interested in quantum mechanics. This is the amplitude for the string to go from an initial configuration to a final configuration. That's the setup. That's the, if you like, after all is said and done, this can pretty much be defined to be the definition of string theory. Well, no, that's too simple. You can generalize the idea. You say, supposing I'm not interested in a string going to a string, but two strings going to two strings, or two strings going to three strings. Then you can generalize it by starting with two strings, ending with three strings, and drawing all the possible surfaces that can interpolate in between them. There's a surface that interpolates between them. There are other surfaces which interpolate between them with different topology. You can put a hole in here. Okay. Perfectly legitimate, but let's concentrate on the ones without holes in them for the moment. You can then ask the question, what is the amplitude to start with two strings, each one in its own given configuration, and end up with three strings also in particular configuration? The answer is the same. The answer is e to the I times the integral over all surfaces which connect the initial state to the final state, e to the I, integral over all surfaces of the action for that surface.
In the simple case, say an electron going from one point to another, is Ex T sigma 0? So it doesn't change.
You mean a point electron?
Yeah, particle doesn't
Well,
change.
a point electron, if you were dealing with it by Feynman integrals before anybody heard of string theory, you wouldn't have any sigma. You would just have tau.
Right.
I think maybe you're asking whether in some limit or other this reduces to the, yeah, that is a good question. The answer is yes. As long as the electron is very much lighter than the string scale, and as long as the energies of the processes are low, then yeah, these things will reproduce Feynman diagrams, ordinary Feynman diagrams. So yeah, they are connected. That would take us more than a little bit. Okay, so that's practically the definition of string theory. Incidentally, if you really mean sum over all surfaces that connect them, including the surfaces that have holes in them of various kinds, then that's pretty much the analog of summing over all Feynman diagrams with all possible topologies and all possible number of loops and so forth. So you have in one simple expression or one simple idea, the sum over surfaces, you have something which is as complex, or as complex is perhaps not the right word, it's much simpler than Feynman diagrams in many ways, but it contains as much the same kind of information as the sum over all Feynman diagrams would contain. Okay, but let's forget these holes for the moment and just concentrate on the structure of this path integral here. There's a path integral for strings. Again, it's a monstrosity for the same reason. Wildly varying surfaces contribute as heavily as straight surfaces and so forth, the integral doesn't converge in any meaningful sense because, again, surfaces which stretch out to Alpha Centauri and come back are no less numerically large in the amplitude than a nice, simple tube. All right, so that means we've got to do something to make this integral make sense. You can do what a serious mathematician would do, would be to try to define a new kind of integral. People have studied that. Or you can do what a physicist would do and say, analytically continue. Analytically continue. Last refuge of scoundrels. Okay, and we are going to be scoundrels. What do? We don't worry about sigma. Sigma is not our problem. It's actually tau which is our problem, as we will see. Let's do the same thing. Let's let tau go to I tau. No, I'm not going to call it S. I'm not going to call it S. It will just get too many variables. I'm just going to tell you. We now make a transformation of variables from tau to I tau. Same trick. When you do, you will pick up an I from here, and you will pick up two I's from here. You won't pick up any I's over here. So let's follow it. Each time you see a tau, you write I tau. Really, tau is becoming S, but I don't want to introduce another variable. So I'm just going to say tau goes to I tau. We change variables to I tau. Then, the first thing that happens is we pick up an I over here. That's good because it'll get rid of this I. But then we pick up two I's down here. What is two I's? Minus. So that turns this into minus here. Same as the minus here. And gets rid of the I over here. Now, unfortunately, I didn't really mean it when I said tau goes to I tau. I meant tau goes to minus I tau, in which case we have an extra minus sign here. Same as for the particle case. Now look at what we have. We have something. Oh, no, I had too many minus signs. Too many minus signs. I've lost control of the calculation.
No, you had I squared.
Yeah.
Okay, that gives you 1 minus 1. And,
Inside my
oh yeah, you had minus I squared, so you end up with plus signs over there.
And plus sign here.
Minus sign there.
Where? Here? Oh, no.
Right in front of you. Whichever one you want, you can get it.
Whichever one you want, you can get. So let's get this one. Let's get that one. It's either tau equals goes to minus I tau or tau goes to plus I tau. The reason I want the plus sign here and the minus signs here is because that allows me to remove the minus signs here and put it out here. Now, why is that a good thing to do? It's a good thing to do because what appears in here is positive. The more wild the surface is, the bigger it's going to be. Even if the surface doesn't fluctuate out to far distances, but it just vibrates a lot, then the x d tau or wiggles too much. Then if it wiggles too much, the x d sigma will be large. If it vibrates too much, the x d tau will be large. If it stretches out to Alpha Centauri, both of them are going to be large and positive. So one good thing of this trick is it made these both of the same sign and both positive. And then e to a minus a positive number is small, or a large positive number. So what does this do? It does the same thing that it did in the particle case. It suppresses the wildly varying surfaces. And it allows you to actually calculate the path integral. I should tell you there's another form of string theory and where what you put in for the action is more complicated but quite beautiful. It's actually, for both the particle and the string, there are other forms of the action which are mathematically harder to deal with, but in a certain sense geometrically very, very highly motivated. For the case of the particle, what you put in is the proper path length as the action. The action is just the proper path length between the initial point and the final point. The proper path length itself. And for the string, what you put in is the space-time area of the world sheet. That's another setup, another formal way to do it. Gives you the same answers, and, but it is more complicated, so I'm not going to do it. If you ever come across the term Nambu-Goto action, the Nambu-Goto action is the action which just says, stick in for the action the area of the world sheet. The other form is sometimes called the Polyakov action, although it had nothing to do with Polyakov. It was invented by me, which Polyakov constantly keeps telling people. People like to get credit, but they like to get credit for what they did. So, anyway, it's called the Polyakov action, this action here.
Things are named after people who didn't do them much more often.
He did do something else, which is related to this, but the other thing he did, which is closely related to this, has some other factors in it, which is also quite beautiful, which was invented by Polyakov. It's called the Liouville action. Liouville was a mathematician who died long, long before even classical mechanics was invented, so don't ask. It's the same reason that Polchinski brains are called Dirichlet brains. I don't know.
Well, that math was around before Polchinski was. I guess Dirichlet strings were around a long time.
Dirichlet boundary conditions on ordinary strings were around a long time. Yeah. Right. That's correct. Okay. That is the idea of the path integral for string theory. Now I want to explain some mathematics. Some trivial math, not trivial, it's nice mathematics. Many of you have seen it before. Let's see. Oh, yeah. Let's take a look at this action and ask what are the things that it's invariant under? What are the things that it's invariant under? What kind of transformations, in particular, of sigma and tau into new variables is it invariant under? Why am I interested in that? Well, I never told you exactly what the choice of sigma and tau were. I didn't tell you how to choose sigma and tau on here. We can just draw it any way we please. Surely the answer can't be the same for any choice of sigma and tau. There must be some rules about what kind of coordinates I can use on the world sheet. But are those rules rigid? They tell you you have to use these particular coordinates, or is there some invariance which allows you to have a variety of different sets of coordinates which will all give you the same answer? That's the classic problem of the invariances of a Lagrangian. What are the invariances of this Lagrangian, but in particular, what are the invariances with respect to coordinate transformations of the sigma tau surface, of the sigma tau parameters? Sigma taus are just labels of points. They don't have any independent meaning other than just labels of points. This one is called George, this one's called Fred, this one's called Harvey. Clearly, the answer can't depend on whether I rename the points Melvin, whatever. Okay, so what are the invariances that are allowed? So we look at this action and we ask what kind of transformations can we make? Let's look at it in a little more detail. Here it is, dx by, in fact, instead of looking at the at the action itself, let's look at the equation of motion, which would come by varying this action. Why? It's as good as looking at the action. The equation of motion that would come from varying this action would look like a wave equation. This is basically the action for a wave equation with one exception. What's the exception? The sign here. Yeah, two positive signs, okay? What's a wave equation? A wave equation would be d second x by d tau squared minus d second x by d sigma squared equals 0. What do you think the equation of motion coming from the from this would be? Close. X is some field on the tau sigma coordinate space. Do you know the name of this equation? It's not called the wave equation. The Laplace equation, two-dimensional Laplace equation. It's the two-dimensional Laplace equation. D second of something with respect to one variable squared plus d second. Usually you see it in a different form. You see the variable x would be replaced by phi, some function, maybe just f function, and tau and sigma would be called x and y. So you'd have an equation like d second f, or d second phi actually, yeah, by dx squared plus d second phi by dy squared equals 0 in 2 dimensions. In 3 dimensions, you would add another one, d second phi by dz squared. I'm talking now not about physics, I'm talking about the formal structure of equations. Do you recognize this equation?
Yeah, it's a
Vibrating drum.
No. Okay, I don't want to get into, yeah, you're partly right, but a vibrating drum also has a time variable in it. Okay, so I don't want to get into vibrating drums, but you're not completely wrong. There's an equation for the electrostatic potential, except in the electrostatic potential, you would have a charge density on the right-hand side. Okay, it's called the Laplace equation, and now it's a Laplace equation in 2 dimensions, except now the variable phi is replaced by x, and the variable x and y are replaced by tau and sigma. But otherwise, the mathematical structure of this equation is the same. The question is, yeah, question.
There you have second derivatives, there you have first derivatives.
Here you have first derivatives. Yeah, but when you have first derivatives in an action, it gives you second derivatives in the equation of motion. Just like having x dot squared in an action gives you x double dot in the equation. That's a good question. Okay, and whether I work with the action or the equation of motion, it doesn't matter. You get 6 of one, half a dozen of the other. All right. I just like this form better because it helps me illustrate a point. All right, now what is a second derivative? Second derivative of x, think of the tau axis as being discrete now. Just to give you a geometric picture of what this equation means. Think of the tau axis as being discrete with little separations epsilon between the neighboring points. What is a first derivative? A first derivative is, let's call this point 1, let's call 1, 2, and 3. A first derivative is closely related to the difference of a quantity at neighboring points. Right? So the first derivative would be like x of 3 minus x of 2. You divide it by epsilon, but this is not the important thing. Let's divide it by epsilon. Epsilon is the distance between the points, and then you let the epsilon go to 0, and that gives you the first derivative. Let's not worry about the epsilons right now. That's not the point. A first derivative is like the difference of something at neighboring points. If that's what a first derivative is, what is a second derivative? A second derivative is difference of first derivatives. All right, so a second derivative is x3 minus x2. That's the first derivative evaluated between these 2 points, minus the first derivative evaluated one step over. So that's minus x of 2 minus x of 1. That's the analog, the discrete analog of the second derivative. Let's see what it is. It's x3, x of 3, plus x of 1 minus twice x of 2. So what is it? It's the sum of the quantities on the outer edges minus twice the quantity in the center. That's a second derivative. Let's look at the thing which occurs in the Laplace equation here. Instead of taking the tau axis to be discrete, let's take the tau sigma plane to be discrete. The tau sigma plane is discrete now. And let's see if we can geometrically identify what this equation means. Let's go to a point over here. A point over here, the second derivative of x with respect to tau is x at this point plus x at this point minus twice x at the center. That's what we just figured out. Let's label the points. 1, 2, 3, 4, and at the center we'll call 5. So d second x by d tau squared, that's x of 1 plus x of 3 minus twice x of 5, right? How about d second x with respect to sigma squared? Oh, did I make a mistake here? Well, okay, it depends on which way I think of tau and sigma. I guess I have in this picture here, I guess I have tau going horizontally and sigma going vertically. I don't usually think of it about it that way, but that's all right. So the second derivative with respect to tau is this one plus this one minus this one. How about the second derivative with respect to sigma? That's going to be this one plus this one minus twice x of 5. So we get to add in plus x of 2 plus x of 4 minus twice x of 5 equals 0. Well, that's not so bad. X of 1 plus x of 3 plus x of 4 plus x of 2. X of 1, 3, 2, and 4. So we get the sum of the x's on the points surrounding x of 5 minus 4 times the sum, 4 times x at 5 equals 0. Another way to say it is that x of 1 plus x of 2 plus x of 3 plus x of 4 equals 4x at 5. 4x at 5. Or yet another way to say it is that x at 5 is the average of the x's on... That's what the Laplace equation says. It's true in higher dimensions also. Okay? That's what the Laplace equation says, that at any point, if you surround it by a square, and even though this thing is on its side, it is a square, any small square, any infinitesimal square, that if you evaluate the field at the sum of the field at the corners, that the field at the center is the average at the corners. Now, the square doesn't have to be oriented this way. It's well known that this equation is invariant under rotations of the sigma tau plane. So you can say it even more geometrically. Take any square oriented in any way, any small square. This is, of course, only true for infinitesimal squares. For any small infinitesimal square, the field at the center is the average of the field at the corners. That's an invariant way, apart from the fact that you have to think about limits, which makes it a little more complicated. Apart from that limiting procedure that you have to do, that's an invariant way to say what the Laplace equation is. and it's an invariant way to describe the equation of motion, the classical equation of motion of this thing here. Okay, so now I can tell you exactly what the invariance structure of the Laplace equation or of this action is. It's the class of transformations of the sigma tau plane which take every infinitesimal square into an infinitesimal square. If, under coordinate transformations of the sigma tau plane, squeezings and mappings of the sigma tau plane, if it takes every small square into a small square, then the Laplace equation will be unchanged in the new coordinates. So if we have some new coordinates, let's call it sigma prime, which is a function of sigma and tau prime, which are functions of sigma and tau. If it is true that any small sigma tau square maps into, this is the sigma plane, sigma tau plane, we map it now to the sigma prime tau plane. Most mappings will not take squares to squares. They'll take squares to something else. But there's a special class of mappings which take squares to squares. Anybody know the name of such mappings? Conformal mappings. Conformal mappings. Now, let me express it another way. If I have a transformation which preserves angles, if all angles are preserved, then it will be a conformal transformation. It will take squares to squares. Why? Well, first of all, let's take the diagonals and map them to the sigma tau plane, so to the sigma prime tau prime plane. There'll be little short segments oriented in some other direction. And let's suppose that all angles are preserved under this mapping. Any angle between two curves becomes the same angle among the sigma prime, the prime plane. All right? Then, first of all, orthogonal angles here will go to orthogonal angles here. This is not true of any old transformation. It's true of some class of transformations, the angle-preserving transformations. Now, we can say something else. Supposing that it had this property of taking perpendiculars in here to perpendiculars, but it stretched things out in one direction. In other words, it made a kind of an elongated kite out of a little square. Then there would be other angles which weren't preserved. These angles over here would be changed. This angle at this corner would not, if this is a 45-degree angle, if it stretched the square in some way, it would not remain a 45-degree angle. So, conclusion, angle-preserving transformations preserve little squares, take little squares to little squares. Yeah?
Wouldn't that just be basically rotational?
What's that?
Wouldn't that just be basically a rotation?
Locally, it's only a rotation, but it can bend the coordinates. No, it's not just rotations. Remember, we're only demanding that infinitesimal little squares remain infinitesimal little squares. But now we can say it without using the word infinitesimal. If the transformation has the property that the angle between any intersecting pair of curves on the sigma tau plane maps into the same angle on the sigma prime tau prime plane, then that mapping is conformal. Conformal mappings preserve, they preserve angles, but since they preserve all angles for sufficiently small shapes, you can think of the curves as being straight lines. And it's easy to prove for sufficiently small shapes, the shapes themselves are preserved. Sizes are not preserved. Sizes are not preserved. A small square over here can map to a bigger square over here. No, I didn't draw. You know what I mean.
Sizes can be preserved,
Sizes
can also be preserved in addition.
then we're talking about the rotations and translations.
Yeah.
Right. That's a much, much smaller class of transformations. Now, here we're talking just about the angle preserving transformations, and they can expand and contract shapes. In fact, they can expand and contract differently in different regions of the plane. Over here, a shape might get stretched to a bigger shape. Over here, a shape might get squashed to a smaller shape.
Question.
Yeah.
Wouldn't this conformal mapping be equivalent to saying the coordinate system is flat?
Nope. Conformally flat, no. I don't know, what do you mean by coordinate system being flat? You mean Cartesian?
That it's not curved, otherwise the angles wouldn't be preserved, would they?
No. No, no. Where is this trick of conformal mappings used?
Mercator projection.
Well, any projection of a map which is intended to preserve the shape of islands, continents, and so forth, small ones, but doesn't care about the sizes of things, that's a conformal mapping. So the relationship between different maps, different projections, both of which preserve shapes, but not sizes, is always a conformal mapping. Yeah.
Yeah. Last week you said, when we were looking at the string scattering,
Mhm.
that at the end you had enough freedom to assume that the string when it split again was kind of in half. And is that related to this?
Yeah. We will. All right, since you asked me, I will tell you right now what the relationship is. Okay. I was going to tell you a little bit about analytic functions, but maybe we'll come back to that. Coordinate transformations, which are defined by analytic functions of complex variables, are angle preserving. We may come back to that. Okay. Oh, incidentally, there is one situation where angles are not necessarily preserved. It's a curious one. You can take any figure with a boundary, let's say a square, a big square now, not an infinitesimal square, a finite size square, and map it by conformal mapping to any shape you like. But in particular, you could map it to a, this doesn't look very square. You can map it to a thing like that. So wait a minute, you said that they have to preserve angles. This doesn't look like it preserves the angles. Well, first of all, it only preserves infinitely small shapes. You can map this to this by conformal mapping, but the corners will not go to the corners. The corners here will perhaps go to these points. Okay, so conformal mappings are tricky. You can map any shape with a boundary to any other shape with the same boundary. This is a theorem about analytic mappings. And inside the region, any small shape will map to a shape of the same kind. Any small shape here will map to a shape of the same kind here in the interior of the mapping. So this is something to know, that you can do some things with changing the shapes of boundaries of regions. Okay, having said that now, let me come to what the point is. Last time we talked about strings splitting and joining. I drew a picture for you where two strings came in, and I indicated that by making a slit. Take a ribbon, make a slit down the ribbon until that slit comes to an end point. Those are two separate strings joining at this point and making one long string, and then continuing again after it splits again like that. There's a one-parameter family of such splittings and joinings characterized by the time interval, or the tau interval, between this point and that point. In the end, if you're calculating a scattering amplitude, you'll integrate over it. You get some integral, and that integral gave you the beta function, the Euler beta function, or the Veneziano amplitude, however you want to call it. We wrote, I described it for you last time, and it gives you the scattering amplitude in string theory. Important fact, but not really terribly central right now. Okay, what's going on in here? What's going on in here is we have a two-dimensional space. We can call it sigma tau. It is sigma tau. And we have at each point in this space, we have an x, not just one x, but several x, a family of x's, x mu, of sigma and tau. And they satisfy some kind of equations. In fact, what kind of equations do they satisfy? They satisfy the Laplace equation. Now, actually, technically, they satisfy the wave equation. But if you do this trick and carry out the path integrals by letting tau go to I tau, then the x's in here satisfy the Laplace equation. What does that tell you? It tells you that you can map, here we have a shape, or here we have a piece of a plane. It goes out to infinity along here. Think of it as being slit down the center here. And think of it as being slit down the center here. What's the topology of this region here? I'll tell you what the topology of this region is. The topology of this region is a circle, but with some special, why is it a circle? Let's start at the center of a circle and work outward with a series of circles. It's a bullseye. Let's start at the center of this and work outward. I can do this in such a way as to cover the whole space by a sequence of closed curves which are isomorphic to the circles. In other words, I have taken the bullseye and deformed it, but without changing its topology. I have changed it into this double strip with these points over here. Now,
Yeah, it depends on what happens out there.
yeah, right. There's some exceptional points. There's some exceptional points, and the exceptional points are the infinite endpoints there and there. But you can do this mapping. This mapping exists, and you'll have to remember that there were some exceptional points which have to be, we have to know what to do with those exceptional points. But the answer is that I don't know what to call this shape. What should we call it? The slit strip, the doubly slit strip. Okay, that's a mouthful. The what?
The Band-Aid.
No. It's cut down the middle there, so it's not quite a Band-Aid.
The sports Band-Aid where they.
Oh, yeah.
Wing,
Yeah.
yeah.
The sports Band-Aid shape. Yeah, good, right.
Butterfly, yeah.
Good. Except that it's the infinite sports Band-Aid shape. Okay, that's not much better than the doubly slit strip. The infinite sports Band-Aid. The infinite sports Band-Aid can be conformally mapped to the circle, or to the disk. To the disk. The disk is a circle, is the interior of a circle. So, That means, in principle, we can take the wave equation, or we can take the Laplace equation, or the action even, of the action of the string, the path integral for the string, the entire setup, and rewrite it in a form in which the x's all live on a unit circle, where the x's all live on a unit circle. There's something special about these 4 points here where the particles came in and went out. And I'm going to eventually tell you what that special thing is. You can map it to here. Of course you can map it to here. But you can map it to here without changing the form of the equation. It's still just a Laplace equation. The Laplace equation for the x's in here is the transform of the Laplace equation for the thing in here. Okay.
And that's because the conformal invariance of the Laplace
Yeah,
equation.
because of the conformal invariance of the Laplace equation. All right. So you could set up the string path integral in a new way by taking a unit disk, thinking of a set of x's which live in the unit disk, and integrating over all ways, all x's that live on this unit disk. In other words, yeah, I think you understand. X of sigma and tau, where sigma and tau are not on the sports Band-Aid, but they're on the disk. Writing the action as the same kind of action and path integrating over the x's in here with some special things going on at these 4 exceptional points. I think I won't get into what there's nothing very complicated about it, and we will get to it. We will certainly get to it. Technically, or in the jargon is, you have to put some vertex operators at the point over here, but we'll come to that. All right. But you could also have stretched that out into other shapes. You could have stretched that out into a shape which looked like this, which went off to infinity. So it looks actually more like a scattering process. There are many things you could have stretched it out into. Okay. Now, let's take a break. Let's take a break. All right. Now, in mapping this problem to this problem, now by this problem, I mean the problem of calculating the scattering amplitudes. There is something that you have to do out at these infinite points here to set up and specify the initial and final states of the particles that are coming in, their momenta, their particle type. Are they the ground states? Are they the first excited states? Somewheres in here, there's some input of information that's above and beyond just saying that there's a Laplace equation in here. That input of information has to do with something or other that we do out near the ends here. I'm not sure how to draw that. Just some input at the end flaps of the Band-Aid. That same input has to be put into this diagram. We have to say what kind of particles, what is their momentum. I'm not going to tell you exactly how to do that at the moment. I will tell you eventually. But it's some operation that you do on each one of these points to inject in a certain amount of momentum and some information about the particle type. Okay? So keep that in mind. All right, now where exactly do we put those points, those 4 points? In this diagram, it's clear where we put them. We put them out at the end flaps of the Band-Aid. In this diagram, it's less clear. And I will tell you what is correct. In mapping this to here, you forget for a moment the ends. You have some ambiguity. For example, you could rotate it. You can do some other things to it. But you also have enough ambiguity that you can arbitrarily choose that there's really only one parameter in the relationship between the 4 points on here. One parameter, all the other, it looks like there are really several parameters. You could arbitrarily pick, by rotating the angles, the position of this point, but then there would be the length or the distance to here, the angular distance to here, the angular distance to here, and the angular distance to here. No. You can find conformal transformations which will move the boundary points around in various ways. And the end result is there is really only, up to a conformal transformation, there's only a one-parameter family of such configurations. And we could describe the parameters by saying, I'll arbitrarily choose left-right symmetry. That's a choice. And I'll also choose vertical symmetry. And I can choose this point over here. Since I've decided to make the diagram both left, right, and up-down symmetric, I have to choose the other point over here, and over here in a completely symmetric way. But that still allows a freedom. Here's one extreme situation. Here's another extreme situation. What determines where you put the points, whether it looks like this, or like that? The answer is the time interval between here and here, which is also a one-parameter family of figures. The time interval, or really strictly speaking, the ratio of the time interval to the separation along here, or the time interval between the tau interval between here and here, is the one parameter that governs where you put these points. You have to integrate over it. Just as we integrated over the time separation, this is part of the path integral, we integrated over the time separation between the joining and the splitting. That translates into a one-parameter integral over, we can choose it in many ways, but in this case, with this particular setup, it's a one-parameter integral over how we choose these points. My fingers aren't big enough to stretch to this configuration here, but if we had two of us up here, I would move my fingers like that, and you would move your fingers like that, and then we'd spread them out and go the other way. That integral is still to be done. Okay. And it's that integral, when you work out the path integral and then integrate over the positions of the points in the right way, that's what gives you the beta function. In this language, the beta function comes from integrating the positions of the injection points. Let's call them injection points. The positions of the injection points over a one-parameter family. There are two extreme situations. One extreme situation is this. The other extreme situation is like this. In this extreme situation, the two input points on the left are close together. In the other configuration over here, this one and this one are close together. Now, these two extremes must translate to some extremes on the Band-Aid. It does. The extreme where the two incident particles appear adjacent to each other and the two outgoing particles appear adjacent to each other, that is the conformal mapping of the configuration where the time interval here is very, very long. And so it looks like these 2 points are much, much closer than the distance between here and here. That's the, if you like, the mapping from the Band-Aid to the circle of the configuration where the intermediate state lasts a long time. It's a situation that manifestly looks like two particles coming in, forming a string that vibrates many vibrations, and then goes off again. That's this limit. What's the other limit? Well, the other limit is exactly the other limit, where the time interval is very, very short. The intermediate state lasts a very short time, like that, and then the splitting occurs, and that's this limit over here. In these integrals, in the various integrals that you do, okay, you can see from this picture that there's some symmetry. From this picture over here, it's hard to see that there's any symmetry between these two extreme limits. Two physically totally different pictures. One, an intermediate state lasts a long time, and the other, an intermediate state lasts a very short time. Doesn't look like there's much symmetry. But from this picture here, you see that, that somehow there is a symmetry, that they must be related to each other in some way. How are they related to each other? Well, that's not the point, though. They're related by the interchange of what we called last time the S variable and the T variable. Remember what the S variable was? It was the sum of the four momenta coming in squared, or the center of mass energy squared. If we label these with momenta, then the S variable, K1, K2, K3, K4, then the Mandelstam variable. The Mandelstam S variable was K1 plus K2 squared, and it corresponded to the square of the center of mass energy. Well, let's write that it's equal to the Mandelstam S variable. This is not the action, and it's not any other S that I used tonight. It's the Mandelstam S variable, S. And it's also equal to the square of the center of mass energy, center of mass. On the other hand, it's quite clear that we've done what we've done in going from here to here. If we've interchanged K1 plus K2 squared, that's the total energy coming in here, with, what was this, K1 plus K3, I think. K1 plus K3. And that's what we called the T variable. That's not the center of mass energy. It's some combination of center of mass energy, E center of mass squared minus M squared, times I think 1 minus the cosine of the angle of scattering or something. But it is just K1 plus K3 squared, where all momenta are counted as coming in. In this form, it's manifestly clear that these diagrams have symmetry between the S channel and the T channel. It's also clear that if they describe particles forming and decaying in the S channel, two particles coming in, forming and decaying, they must also describe a process where the two incoming particles are replaced now by one incoming, one outgoing, and a particle is exchanged. Not the creation and annihilation of a particle, but an emission and reabsorption at the other side of the diagram. So that's what was so fascinating about these structures, is that one structure, one simple structure, one integral, but one basic principle was accounting for both the S channel and the T channel particles. The S channel particles were somehow associated with long diagrams like this, and the T channel ones were short ones. But we don't have to interpret. We just say the integral was symmetric under S goes to T. And so whatever was there in the form of S particles formed by K1 plus K2 coming together, there was also T-channel objects which were formed by K1 and K3 coming together. That was called duality. That was the first duality, the duality between the S channel and the T channel. Now these days it's called channel duality. Channel in this case means either, well, it's clear what it means. And it's called channel duality, and it was the first sort of, at first it was a miracle. At first, when thought about in terms of Band-Aid diagrams, it was a miracle that there was a symmetry between S channel and T channel. It was very quick that it was realized that this was because of conformal symmetry, and that you could map it to this more symmetric situation. But at first sight, it just looked like a miracle The trouble with understanding miracles is it always has the same effect. You know, you may now understand it, but you no longer go gaga over it. And,
When was it?
1969.
If you were to draw that second one, the one that goes down, I can understand how the top one corresponds to the Band-Aid. Is there a Band-Aid that corresponds to the second one?
Well, yeah, you could have drawn the diagram the other way. You could have drawn it this way.
Time would still be going horizontally?
No. Yeah, you could have, well, yes. Well, no, time comes in here, well, no. You could, in that case, you could not have thought of time as running horizontally. You would have to say this was the deep remote past over here, and this was the deep remote future over here. But you could have drawn it that way.
For some reason, I think of the time that they're together being related to the coupling constant.
No. The time that they're together, you have to integrate over. That's something you integrate over. I think what you're trying to say is that the probability for it to decay is related to the coupling constant. Yeah, but in either case, no matter what, that just means you have to put into the integral the coupling constant. And, but no, these diagrams, the coupling constant just comes in as a multiplicative factor. And, right. Okay, I think that's enough for tonight.
For more, please visit us at stanford.edu.